Here we'll discuss the relevant components providing voltage to the base terminal of the transistor, allowing the device to operate accordingly. First we'll cover why the transistor needs a voltage at this location. Now the transistor in the LPB1 circuit is a bipolar junction transistor. Even though BJT transistors are current controlled devices, they need a voltage present at their base terminal. This forward biases the PN junction between the base and emitter within the transistor. At this PN junction there is something known as the depletion region. This region prevents current flow through the device. To overcome this depletion region and permit current flow, a voltage at the base terminal is required. The amount of voltage required is dependent on the material the transistor is constructed with. A germanium transistor requires a voltage between 0.2 and 0.3 volts. Alternatively, a silicon transistor requires a voltage between 0.6 and 0.7 volts. The transistor utilised in the LPB1 is a silicon transistor, so a value around 0.6 to 0.7 volts is required. Using a multimeter, you can measure the precise voltage required at the base. With your multimeter set to the diode mode and attaching your positive lead to the base and negative lead to emitter, you can take a reading. From this photo, you can see my multimeter readings. Now we know why the transistor needs a voltage at the base, we can take a look at this in operation within the LPB1. Now the signal coming from your guitar will present a voltage value at the base of the transistor. However, a guitar signal ranges between 0.1 and 0.3 volts roughly. And as previously mentioned, it's an AC voltage, which isn't optimal when powering an active device. So we need to supply the base with a DC voltage. This can be achieved through different schemes. In the LPB1, a voltage divider is utilised, using the resistor seen here. This scheme alludes to the voltage divider bias we previously mentioned when naming this circuit. Let's take a closer look at a voltage divider circuit in isolation. Utilising these two resistors in series, we will have a total of a 9 volt drop between the power rail and ground located at resistor 2. At the node where these two resistors meet, there will be a voltage that's proportional to the ratio between the two resistor values. Changing the resistor values will change this ratio, having an impact on the voltage found at this node. You can calculate the voltage at the node by the following. The power supply multiply R2 divided by the sum of both resistors. So if we plug the component values from the LPB1 into this equation, we have a value of roughly 0.8 volts present at the base. So this is how we bias the base of the transistor, meaning we have provided the base terminal with the voltage it requires, and simply put, making sure the transistor turns on. Identifying how this is achieved within circuits is a useful part of circuit analysis, and is always a consideration when utilising BJT transistors. With this value, we can easily calculate the voltage at the emitter terminal of the BJT. As we use 0.7 volts to forward bias the PN junction between the base and emitter, the emitter voltage will sit 0.7 volts less than the voltage found at the base terminal. So the voltage at the emitter in this case will be 0.8 volts minus 0.7 volts. We therefore have a voltage at around 0.1 volts at the emitter. In the next session, we'll look at the current gain of the transistor, as well as calculating the current values at each of the terminals on the transistor. See you there.